these sampling distributions...
The Seattle Epidemiology Research and Information Center, in collaboration with the Department of Veterans Affairs, the VA Employee Education System, and the University of Washington Department of Epidemiology, present the 2002 VA Epidemiology Summer Session.
Okay, well, welcome back. We did spend the first half of this period looking at methods for statistical inference that focused on estimation, so using estimation. Now we'll spend the remainder of the period looking at the role of hypothesis testing. There's a relationship between hypothesis testing and confidence interval estimation. So we'll see that the inferences that we make based on one or the other should agree. If they don't, we've made a mistake. What we'll do now is look at the rationale behind hypothesis testing and how it incorporates sampling distributions. We'll look at the steps that we take in hypothesis testing. We'll focus on the possible mistakes or errors that can be associated with hypothesis testing. And of course, we'll define the ubiquitous p-value and how we can set up a test statistic and look at this through some examples. So the rationale for hypothesis testing is that we really would like to use our data from a sample to provide evidence to either refute or accept a hypothesis. So hypothesis testing really is an aid. It's an aid to a clinician or researcher in making a decision, in making a statistical decision regarding a population or two populations based on a sample or two samples. So the underlying premise is that if a hypothesis or a guess that we make regarding a true but unknown population parameter is true, how likely is it that we would calculate or obtain the value of the sample statistic that we obtained from our sample? So the premise is that we've conducted just one study with one sample, and we're interested in assessing how likely the value of that sample statistic is, or how unlikely it is if a hypothesis that we make is true. And then we go on to reject or fail to reject the hypothesis on the basis of our sample data. Now, how we put this into practice is through the steps of hypothesis testing. First, we'd select the probability model for the observed data. We've been spending most of our time on one model, and that's the normal probability model. We'd set up a null hypothesis that we can term as H0, and an alternative hypothesis that we'll term as HA. And then we can do either a two-sided or a one-sided test depending on the directionality. And we'll talk about whether or not we'd prefer a two-sided or one-sided test as we look at some of the examples. So once we've set up the probability model, we've set up a null and alternative hypotheses, we can select the test statistic Z or T. And again, the use of the T is when we don't know the true population standard deviation. Otherwise, we would use a Z. The next steps then are to make a decision based on a decision rule or a rejection region. So this is based on choosing a significance level alpha, where alpha is the probability that we place in the tail or tails of the distribution. And we'll see that once we choose the significance level, it determines the values of the critical region. And based on our data, we'd calculate a test statistic and see whether or not it falls within the critical region or outside of the critical region. Now, it hopefully makes some sense that what we're terming as the critical region is out in the tail of the normal distribution where there's very low probability. And those that don't fall in the critical region are in the center part of the probability distribution where there's high probability. So we'll see how we can use the underlying normal probability distribution, set up a critical region, calculate a test statistic based on our data, and then make a statistical decision and conclusion. So, suppose that I was looking at the sampling distribution of the sample mean x bar. So, and suppose that my null hypothesis was that the true population mean mu was equal to some value, and I'll just use the symbol mu naught to represent some value. So that value that I'm hypothesizing is going to be based on a previous study based on done in a different locality potentially, a smaller study based on pilot data. And I can draw a diagram then of the sampling distribution. Remember what the sampling distribution is showing. It's showing a distribution of the values of all possible sample means that could be gotten theoretically with a sample of size n. Now remember that some of the values of the sample mean will have very high probability. Those are the ones that are close to the center of the distribution. Other values are possible but have very low probability. Those are ones that are out in the tails of the distribution. And when I do a study, I calculate one sample mean, and I'm looking to see whether it falls, where it falls under this distribution, either in the central part of the distribution or out in the tails. So if I transformed that sample mean, the distribution of the sample mean, to a z, and how would I do that? Here's the statistic. In order to transform to a z, I would subtract the hypothesized mean of mu naught, and I'd have to divide it or rescale it by the standard deviation that corresponds to the sampling distribution. It's not labeled in this slide, but what's the spread of values of the sample mean based on the theoretical sampling distribution? Let's see. One answer? The spread? So if I asked what's the standard deviation of these possible sample means? Well, some of you are answering that about 68% would be within plus or minus 1 standard deviation of the mean. But actually what I was looking for was that the spread is given by sigma over the square root of n. So the spread in these possible values of sample means depends on two things. It depends on the true population standard deviation as well as the sample size. So if I transform to a z, I would subtract the mean, divide by sigma over the square root of n, and then I would see that those values that are in the center of the distribution would be ones near a z value of 0. Those that are out in the tails of the distribution would be z's less than negative 1.96 or greater than positive 1.96 if I choose a significance level alpha equal to 0.05. So typically one uses a significance level of 0.05 because then that means the probability in each tail is only 0.025 and the center probability is equal to 1 minus alpha or 0.95. So the aim is that we'll consider values that fall out in the tail of the distribution, those that have a probability less than 5% to be unlikely to occur just by chance alone, whereas values that fall in the center of this distribution, where the probability is 0.95, have likely values. So the critical region will be z values that fall in the tails. That's where we'll reject the null hypothesis in either of the tails. And where we'd fail to reject the null hypothesis is in the center of this z distribution. That corresponds back to the center of the distribution that's centered around this hypothesized value of mu naught. Okay, so I'm setting this up theoretically, and then we will look at an example. But the statistical decision then will be to either reject the null hypothesis because the value of the test statistic is so unlikely to have occurred out in the tail of the distribution when under this assumption that the null hypothesis is true, or we'd fail to reject, in other words, accept the null hypothesis because the value of the test statistic derived based on our data is it's likely to occur. So let's look at this diagrammatically. So the result of the hypothesis test is that There's an acceptance region where we'd say in the body of this distribution, these are values that are likely to occur. Ones out in the tail of the distribution are unlikely. So I can define alpha either by placing all of the alpha in one tail, or have a two-sided test where I split alpha divided by 2 in one tail and alpha divided by 2 in the other tail. So the critical regions would be those highlighted in yellow. The acceptance region is that's not highlighted. Now, suppose I have a null hypothesis that the true mean is equal to some value mu naught, and I have an alternative hypothesis that the true mean in the population is equal to some other value, mu a. So does it make sense to think of one distribution, sampling distribution, that's centered at mu naught, and the alternative is centered at mu a? So here's our two guesses about the truth. One is that the mean is some lesser value, mu naught. The other guess is that the mean is actually some higher value, mu a. So if I set up a rejection region that's out here in the tail, what are the possible findings or results that can occur? I might actually reject the null hypothesis when it's actually true. So these are values of the sample mean that are, or the test statistic that are unlikely to occur just by chance alone, but are possible. On the other hand, I might fail to reject the null hypothesis because the test statistic falls in this acceptance region, but it might really have been from a population that's centered at a higher mean. Now, I know that this is sometimes hard to look at without having an example, but let's first say what the 4 possible outcomes are, and then we'll put an example to this. So what are the possible truths? There are 2 possible truths. Either the null hypothesis is true or the null hypothesis is false. And the conclusion that I make based on the data from my sample is, again, we're sort of making this a dichotomous decision. We either reject the null hypothesis in hypothesis testing, or we don't reject the null hypothesis. So if the null hypothesis is really true and we don't reject it, that's a correct conclusion. If the null hypothesis is really false and we reject it, that's a correct conclusion. But then there are 2 types of mistakes we can make. So those 2 types of mistakes are referred to as a type 1 error and a type 2 error. Type 2 error is the error that we make when the null hypothesis is really true, but we reject it and say it's false. That's called a type 1 error. The other mistake is when the null hypothesis is false, but we don't reject it based on our statistical test, and we've committed a type 2 error. So if I went back to this diagram, alpha is the probability of a type 1 error. It's the chance of rejecting the null hypothesis when the null hypothesis is really true. Beta is the probability of a type 2 error in which we fail to reject the null hypothesis when the alternative is really true. So we have the possibility of making correct conclusions. We have the possibility of making some mistakes. And so just to outline again the definitions of type 1 error. Type 1 error is when you reject a true null hypothesis. Alpha is the probability of a type 1 error. Type 2 error is not rejecting a false hypothesis. Beta is the probability of a type 2 error. And then statistical power is defined as 1 minus beta. It's the probability of correctly rejecting a null hypothesis. So if I go back 2 slides and look at this alternative hypothesis, the power is the probability to the right of this line. So under the alternative hypothesis, the area under the curve to the right of this cut point is 1 minus beta, or the power of the statistical test to actually detect or reject the null hypothesis when the alternative is true. Okay, so a little bit more just of development, theoretical development. If Alpha was the probability of a type 1 error, and beta was the probability of a type 2 error, and we said that power is the statistical power is the probability of correctly rejecting the null hypothesis when it's false. Then our aim, as usual with mistakes, is to try to minimize or keep the type 1 error small and also keep the type 2 error small. So if the probability of type 2 error is minimized, then that will maximize the statistical power of the test. Now, this might be a good time just to talk about the fact that we always do want to keep our mistakes at a minimum in everything, but it's a toss-up. We know that if we tried to minimize alpha and minimize beta at the same time, what you expect would also happen to our needs. So if we tried to keep the sample size, the errors small, what might happen to the sample size that we're required to have? It will become very large, and we will talk more about that. So our aim is, though, to do the best we can in minimizing alpha, minimizing beta. If we had to make a choice between alpha being smaller than beta or beta being smaller than alpha, what might you choose to do you imagine? Which type of a mistake are you more willing to make? So you're more willing to be wrong by saying by failing to reject the null hypothesis as opposed to rejecting the null hypothesis when it's actually true. So we will spend more time on that, but that's typically the trade-offs in minimizing errors. Okay, one more definition is that of p-value. So everybody knows about p-values, and we will, in this course as well, talk about p-values, but we've also talked about another type of statistical inference already, and that was with confidence interval estimation. My preference is to quote a confidence interval more so than a p-value. And sometimes you can do both, show the confidence interval and quote the p-value. But we still see p-values, so we'll define p-values, we'll see how they're calculated, and we'll look at the correspondence between a confidence interval construction and a p-value calculation. So the p-value for a hypothesis test in plain English is the probability of obtaining the value of the test statistic that you obtained from your data, or one more extreme, just by chance alone, given a null hypothesis that you're setting up is true. So we'll see that it can be a one-sided or a two-sided p-value. Some common interpretations of values of p-values is that a p-value that's less than 0.05 is considered statistically significant, whereas a p-value that's greater than 0.05 is considered not statistically significant. Now, these are typical interpretations of a p-value. Now, is a p-value of 0.04 very different than a p-value of 0.06? No. So there's a guideline that a p-value of 0.05 is considered to be statistically significant. But we'll talk about the fact that there are differences sometimes between statistical significance and clinical or practical significance. And we might not always use a firm cutoff of 0.05 in our decision making. So we have only a little bit more to set up before we can look at an example. But we've talked about the critical region where we would reject the null hypothesis versus fail to reject. It's all going to be based on the calculation that we perform called a test statistic, which in general form takes the value of the sample statistic that we derive from our data, subtracts the hypothesized value based on our null hypothesis, and then divides by the standard error of the sample statistic. So if we recall back when we were looking at the sample mean, the sample statistic was x bar, the sample mean, and the standard error of the sample statistic was sigma over the square root of n. Or if we didn't know sigma, the standard error was calculated as s over the square root of n. So in order to calculate this test statistic, we need the sample statistic, we need to have a hypothesis, and we need to be able to calculate the denominator, the standard error of the sample statistic. And this is in general terms. We'll look at it first with just a single sample mean, but we can expand it to proportions, to two samples, two sample means, and two sample proportions. So if we start with the first scenario of a test statistic for a single sample mean, we may have a null hypothesis that the true but unknown population mean is equal to some value, and that value is one that is an educated guess based on a previous study or pilot data. If we actually knew the population standard deviation, then our test statistic would be a z. We'd set up the z as the sample mean minus that hypothesized value divided by the standard error that we get by taking sigma divided by the square root of n. But most of the time, the population standard deviation isn't known, so instead we would use a t because of our lack of knowledge of the true population standard deviation. The t looks very similar. What's different? The standard error. We're substituting in our best guess at the standard deviation by using s, the calculated sample standard deviation. But keep in mind, when n is large, in the order of 25 or 30, the value of t approaches that of a z, and we could use a z instead. In theory, it's still a t because of this unknown population standard deviation that we're estimating by sigma. Okay, now we can expand this as well to testing a population proportion. So if our null hypothesis then is a question regarding the true population proportion, the statement of the null hypothesis is that the true population proportion p equals some value we're hypothesizing, based again on pilot data, previous studies. So it's always going to be a z as the test statistic, but it takes the sample value. It's a variation on the same theme. Takes the sample value minus the hypothesized proportion. Now the standard error is going to be the square root of p times q over n. What do we use for p and q? We use the hypothesized value. And so if we hypothesize that the true value is equal to some value p naught, then q naught is going to be equal to 1 minus that value. And we'll look at this with an example. Okay, so let's go back to means. And we'll go back to the sample of 25 infants whose mean birth weight was 2,500 grams. And suppose that we know, in other words, that we hypothesize that full-term infants have a birth weight of 3,000 grams. And suppose we're interested in whether or not we have sampled from a population of full-term infants. So we've taken a sample of size 25. We're hypothesizing that we have sampled from a population where the mean birth weight is that of full-term infants, 3,000 grams. And we're interested then in answering the question, can we conclude that we have sampled from a population of full-term infants based on the evidence in our data? So our null hypothesis is that the true but unknown mean of the population that we sampled from is 3,000 grams. We took a sample of size n equals 25. The mean of the sample, x bar, is 2,500 grams. We're going to suppose, just for the moment, that we know the true population standard deviation and that it's 1,000 grams. Because of our knowledge of sigma, the test statistic would be a z. And we would calculate it by taking the sample mean of 2,500 minus the hypothesized value of 3,000 divided by the standard error, that's 1,000 divided by the square root of 25, and we would get a z value of negative 2.5. So we'd have to ask ourselves, is z in the rejection region or not? Remember that using the z table, if we set a significance level, or the probability of a type 1 error equal to 0.05, then the rejection region would be z bigger than 1.96 or z less than negative 1.96. Where does our value of z fall? Out here in the rejection region in the tail, where z was equal to negative 2.5. So based on that, we see that we would reject the null hypothesis. We'd conclude that we aren't able to conclude that the sample's drawn from a population with a mean equal to 3,000 grams. In other words, our conclusion would be that it doesn't appear likely that we sampled from a population where the mean was 3,000. Based on our sample mean and based on the test statistic, so based on our mean of 2,500 and a z of negative 2.5, it appears more likely that we sampled from a population in which the true population mean is something different than 3,000 grams. Based on our data, we could even conclude that it might be something less, Now, how would we calculate a p-value to go along with our statement? The p-value is just the probability of observing what we did or something more extreme. In other words, the probability that z is less than negative 2.5, or just by the luck of the draw, we could have had something more extreme in the other direction, a z greater than 2.5. So I would look up the z value in the table. I would see that the probability of z being less than negative 2.5 is about 0.006. And if I added 0.006 from the other tail, I'd see the p-value is about 0.012. So how would we interpret that p-value? I'll take you back to this. We've hypothesized that the mean was 3,000. What we saw was actually a sample mean that was 2,500 out here in the tail of the distribution. The p-value is calculating what's the probability of observing the sample mean that I did of 2,500 grams or something more extreme, meaning less, in either direction. So the 2,500 gram mean translated, we saw, into a z of negative 2.5. So I would calculate the probability of negative 2.5 or something smaller, probability of positive 2.5 or something bigger, and our interpretation of the p-value is that it's the probability of observing a sample mean, such as the one I observed, of 2,500 grams, or something more extreme in either direction, just by chance alone, if the true value of the population mean was 3,000. So in other words, what are we saying? We're saying it's the chance of getting what we got or something more extreme just by chance alone if this hypothesis was actually true. So if the hypothesis was actually true, what are our chances of observing the data that we did? Not very probable. The p-value of 0.012 tells us that the chance of getting what we observed, the probability of observing what we did just by chance alone, is less than 12 out of 1,000. So only 12 out of 1,000 times would we observe a sample mean of 2,500 grams or something less, or in the other direction, something more extreme. So our conclusion would be based on either the p-value or the fact that our value of negative 2.5 fell in the rejection region, is we'd reject this hypothesis and conclude that we sampled from a population with a population mean different from 3,000 grams. Does that make sense? We have time for a question if it doesn't. Okay.
If we know that the mean birth weight is 3,000, we've observed in our sample it's 2,500, why do we use a two-tailed t-test?
Okay, so that was a good question. The question was if we knew that the mean was 3,000. But in fact, we don't know that the mean is 3,000. We're hypothesizing that it is. So we're hypothesizing that based on previous data, full-term infants have a mean weight of 3,000 grams. We've taken a sample from an unknown population, and we don't know what the true mean is in that population. So to be conservative, we would do a two-tailed test in which our rejection region is in both directions, because we don't know if we're sampling from a population that has a lower mean or a higher mean. Now suppose that we actually took a population, we sampled from a population that we knew was of premature infants, if it was a population of premature infants, we might say that we know there's no way that, that the population that we sampled from has a mean birth weight that's greater than that of full-term infants. And in that case, we might be willing to place our rejection region all in one tail of the distribution. But it's only in that special scenario where we know there's no physical or biological way in which it could go in the other direction that we would choose to do that. So the most conservative is always to say, I'm going to take my chance of making a mistake and split it among these two directions. So by setting a significance level of 0.05, I'll split it into two tails and place 0.025 in each of the tails. Okay. Any other questions? Okay, so we looked at this under this big assumption that we actually knew the standard deviation of 1,000 grams. But again, if we don't know the mean of the population that we're sampling from, we most certainly don't usually know the true population standard deviation. So what we would do instead is calculate the standard deviation from our data. So suppose we calculated it and the sample standard deviation was 900 grams. Now the only thing that changes is our test statistic. Since we don't know sigma and we use S instead, the test statistic is now a t. All that changes is our denominator. The t value is now negative 2.78. When the sample size is large, we know that the t approaches a z, but for the moment, let's look at what we would get if we actually used a t. So remember, the sample size was 25, so the degrees of freedom are 24. And if we looked up the t value that corresponds to alpha of 0.05, split in two tails, in the t table with 24 degrees of freedom, that value would be 2.06 and negative 2.06. Not very different from 1.96 and negative 1.96, just a little bit. So what we would see, though, is that our p-value then is closer to 0.01. In other words, only 10 out of 1,000 times would we observe a sample mean of 2,500 or something more extreme if the true population mean was 3,000 grams. So where does our test statistic fall? Remember now it's been calculated as negative 2.78. It falls into the rejection region corresponding to a p-value less than 0.05. Just as we saw when we used the z statistic. So our conclusion would remain the same. We'd reject the null hypothesis, conclude that we're sampling from a population that has a mean different from 3,000 grams. Okay, so here are the conclusions. Based on our data, and this is important because it's always just based on our data, it's unlikely that we sampled from a population of infants with a true population mean birth weight of 3,000 grams. Based on our data, it looks like we probably sampled from a population where the mean population mean birth weight was less than 3,000 grams. And if we looked back at what our 95% confidence interval had been from last time, we would have seen that our 95% confidence interval does not contain what value? 3,000. So the results of the p-value, whether the test statistic falls in the rejection region, and our interpretation of the confidence interval should all agree and point to the same conclusion that it's unlikely, based on our data, that the true population mean is 3,000 grams. So just a few things to reiterate. This p-value is only a guideline. It's only a guideline based on the, under a hypothesis of a certain value that just due to chance alone we would expect test statistics that are out in the tails of the distribution 5% or less of the time. So it's an arbitrary guideline because we're really saying that 5% or less is unlikely and more than 5% is likely. Is 0.01 less likely than 0.05? Yes. So, 0.01 could serve as a guideline as well, but typically a 0.05 cutoff is used for statistical significance. It's only a guideline. It causes you to sort of make a black or white hard, and dry decision, which is a drawback of hypothesis testing. A confidence interval actually is much more informative because it gives you a range of values. Based on your data, you form an interval that provides a range of values that could be consistent with the truth. And one needs to also keep in mind that any conclusion that you make has statistical implications but also practical implications. And I think somebody yesterday told me that, Jeff, you should remind me what it was, but
Statistics should never replace judgment.
right. And I agree with the statement that statistics should never replace judgment. So in other words, you might get a statistical decision that's at odds with your clinical or practical judgment. And statistics is a tool, it's an aid, it shouldn't replace your practical and clinical judgment. We're going to see more when we talk about sample size, but we've seen some already that the decisions that you make reflected in both your confidence interval constructions and the p-values that you might get from hypothesis tests are related to sample size. So it is true that you can make anything statistically significant if you increase the sample size sufficiently. Is it practically significant? Not necessarily, but you can make anything statistically significant. So in summary, then, we've looked at hypothesis testing as another method for making a statistical inference. Certainly, point estimation and confidence interval estimation was the first one we looked at. What are the steps in hypothesis testing? We state a null hypothesis and an alternative hypothesis. We use our knowledge of sampling distributions and subsequently the way we construct our test statistics to determine whether or not our observed sample statistic was likely or unlikely under this hypothesis. So in other words, another way of stating this is if the null hypothesis is true, the one that we've stated, we're calculating the probability of observing what we observed or something more extreme just by chance alone, and we're looking at whether what we observed was likely or unlikely under this assumption of the null hypothesis. So the ways we do that are by setting up a critical region or alternatively calculating a p-value, but we need to recognize that there are errors associated with hypothesis testing because we do set alpha, the probability of a type 1 error, and depending on the alternative hypothesis, we also have a probability of a type 2 error or beta. So this is, again, in summary, to say that the statistical decision that we make with hypothesis test really is just a guideline based on the p-value, where a p-value that's less than 0.05 says if the null hypothesis were true, we're really unlikely to observe the data that we observed. This is what we would consider to be statistically significant, whereas a p-value greater than 0.05 is one that we're likely to observe, a sample statistic that we're likely to observe if the null hypothesis is true. So this is where we will end the formal lecture today. Let's review yesterday's homework. The first problem was looking at two different treatment groups, drug A and drug R, 19 observations in drug A and 17 subjects treated by drug R, and we were interested in time to clearance. Just to review some different summary statistics, one could certainly look at the median or the middle time to clearance. It was 130 in one group and 253 minutes in drug group R. We could certainly calculate another measure of central tendency, the mean or average. So the sample mean, if you recall, is just the summation of all of the times divided by the total sample size. For the first drug group, the mean time to clearance was 133.9 minutes. For drug group R, it was 267.4 minutes. So we can certainly see that the central tendency tended to be higher as expressed by both the median and the mean for drug group R compared to drug group A. Measures of variability are the sample variance and the sample standard deviation. And just to reiterate, the sample variance is calculated by taking the sum of the squared deviations of each observation from its mean clearance time divided by the sample size minus 1. So this requires some tedious calculation by hand, but if we took each observation minus the mean and squared it, summed them up, and divided by 19 minus 1 for drug group A, we would see that the sample variance was 503.8 minutes squared, and the square root of that is the sample standard deviation of 22.4 minutes. Similarly, we could calculate the sample variance for drug group R as 4,448.9 minutes squared, and the square root of that is the sample standard deviation for drug group A, R, of 66.7 minutes. So in terms of variability in the times to clearance, we see that there's much more variability in drug group R than in drug group A. These were simple descriptive measures of central tendency and variability. Another concept that we looked at was that of probability, or ways of calculating the occurrence or the chance or likelihood of certain events or characteristics. The next problem looked at cross-classifying 1,820 individuals as a result of an X-ray screening test for tuberculosis in their true disease status, either having tuberculosis, indicated as yes, or no. So here's a 2x2 or contingency table that cross-classifies each of those 1,820 individuals. There were a couple of different types of probabilities that we could calculate. One is sensitivity, the sensitivity of the X-ray test, which is defined as the probability of a positive X-ray given an individual is diseased. So this is a conditional probability that focuses on the subgroup of individuals who truly have the disease of tuberculosis. And we're looking at the performance of the X-ray in terms of the positive results out of the total of 30 who did have the disease. So the sensitivity is the probability defined by 22 divided by 30, or 0.73. Specificity, on the other hand, looks at the probability of a negative X-ray result in the group of individuals who are not diseased. So we're focusing on the subgroup of 1,790 individuals without tuberculosis. The number of those individuals who had a negative X-ray was 1,739. So the specificity of the test is 1,739 divided by 1,790, or 0.97. So we would say that X-ray as a screening test for tuberculosis has a 73% sensitivity and a 97% specificity. There were two other conditional probabilities that are used to characterize screening tests. One is the positive predictive value, which looks at the probability of disease in those who test positively. Here, this is 22 divided by 73, or 0.3. Another characteristic is that of negative predictive value, which looks at the probability of no disease in the group of individuals who test negative. So 1,739 divided by 1,747, or 0.995. Yesterday, we looked at one other extension of probability, and that was looking at probability distributions, which look at the description of probability associated with all possible values that a variable may take. And we looked at the normal distribution as one that allowed us to look at a continuous measure centered at some mean with mu and a standard deviation sigma. So first we looked at probability distributions describing populations. And this example asks us to look at considering individuals to have common colds approximately 2 times per year. So if the random variable of interest, x, was the time between colds, suppose you were told that in a population of individuals, the mean time between colds, mu, was 160 days, and the standard deviation, sigma, was 40 days. By the characteristics of the normal distribution, if the time between colds was actually normally distributed, we would be able to say that about 0.68 of the probability, or 68% of the area under the curve, falls within one plus or minus 1 standard deviation of the mean. In other words, approximately 68% of the population would have times between colds that ranged between 120 to 200 days. Approximately 95% would have times between colds that range between 80 to 240 days, and almost all of them would range within plus or minus 3 standard deviations of the mean. In other words, between 40 up to 280. Now, we could ask a couple of questions regarding that distribution. We could answer questions such as, what's the probability of going 200 or more days between colds for individuals in this population? And first, we could write this as the probability that the time between colds X is greater than 200. We would see that that falls in the area which is 2 standard deviations away from the mean. In other words, we could reason through this and say that this probability is about 16%, or 0.1587. But the other way is to transform this to a z by subtracting the mean of 160, dividing by the standard deviation of 40, and this translates to the probability that z is bigger than 1. Looking at the tabled value, we would see that probability is about 0.16. Similarly, we could say, what's the probability of going 365 or more days? We would look at this as a probability that the time between colds is bigger than 365. We would see that by transforming to a z, the same probability can be seen for the probability that z is bigger than 5.1. That falls out here in the far tail of the distribution, where the probability is approximately 0. And lastly, let's look at the probability of going less than 80 days between colds. Here we would see that the probability of less than 80 days is 2 standard deviations below the mean of 160. We could reason through this that this is about 2.5%, or we could transform to a z by subtracting the mean of 160, dividing by the standard deviation of 40, and we would see that that's the probability that a z is less than -2. By looking that up in the z table, we would find a calculated probability of 0.0228. So the chance of an individual in this population going less than 80 days between colds is less than 2.5%. So we reviewed the concepts of summarizing data, looking at probability, and as well then looking at a population probability distribution formed by a normal probability distribution centered at some mean, mu, and some standard deviation, sigma.
Good day. My name is Gailiber. I'm the director of the VA Summer Epidemiology Sessions here in Seattle, Washington. I'm also a VA career scientist and a professor of epidemiology and health services at the University of Washington. Epidemiology research requires data, and it's important to have good data. And so today we're going to be talking with Dr. Chuck Maynard a little bit about data that's available in the VA. Dr. Maynard is an associate professor of health services. He's very active in cardiovascular research, and for the Seattle Epidemiology Research and Information Center, he is the data manager. So we'd like to first go to Dr. Maynard and ask him about the data in the VA. Is it a good source? Is there one place to go when you need data?
Thank you, Dr. Riber. In the last 3 years, there's been tremendous growth in the amount of information available about VA databases, and it's contained in a website for the Veterans Affairs Information Resource Center. The web address is www.virec.research.med.va.gov, and is a tremendous source of information about VA national databases.
So if I want to learn what's available, the types of databases, the types of information in the databases, I can go to VIREC. How will I know what's inpatient data, what's outpatient data? How do I figure out the system there?
Well, one of the best introductions is this presentation given by Dr. Denise Hines, who was the director of VIREC at the 2002 National Meeting of Health Services Research and Development and for the VA, and would recommend this slideshow of about 70 slides for you to preview, and it gives you a really pretty good introduction to what's going on with VA national databases.
So there are different databases for inpatient care, different databases for outpatient care, different databases for pharmaceuticals, for interventional devices. There's a lot there. How do I really, once I look at Denise Hines' presentation, what's my next step?
Well, the next step probably is to go to the inpatient and outpatient data resource guides for the year 2000. And what these documents contain is, on the inpatient side, or what's commonly known as the patient treatment file, a listing of all variables in the 3 major files which have to do with the main inpatient file, which contains demographic information as well as diagnostic information. There is a second file on procedures that are performed outside the operating room, and a third file that contains procedures performed in the operating room. And all of the procedures are identified by ICD-9 codes. And this document, the inpatient document, is about 150, 60 pages and contains listings of all the variables, what the variables mean, and how the variables have changed over time. And a comparable document exists for the outpatient care files, which are much larger files, as you might imagine, since over 4 million veterans per year receive care in the VA. And there are basically 3 major files there. There's a visits file, which describes the clinics to which visits occurred during a given date and time. A second file, which examines diagnoses assigned during those visits. That's been in existence since 1997. And finally, a file of procedures, which contains current procedural terminology coding to identify various procedures performed during a given visit. So I think by examining these documents, one can get a pretty good idea of what's actually exists in the files.
So these files wouldn't be open to just anyone. Is there some special permission that's needed in order to access these files?
Well, these files exist on the Austin mainframe computer located in Austin, Texas, and in order to have access to these files, one has to apply for permission. And probably the best source of how to go about doing that is this section on the website about for new users of VA data. And it contains a nice overview of how one goes about applying to use Austin, the necessary forms and explanations about the signatures required to get permission. So if one follows these little various links in this website, I think you can accomplish the task of getting access to Austin and beginning to learn how to use Austin to obtain the information you need.
Now, I understand these are pretty complex files, and someone with experience would be inordinately helpful. If a new user wants to use these files and needs some advice or some guidance, who should they contact?
Well, there are a couple sources one can go to. The Austin facility itself does give training on, number one, how to use a mainframe computer, and number two, it does give some basic training in SAS, which is the file format in which all of these databases are stored. So the use of Austin presumes, first of all, some knowledge of working on an IBM mainframe with the MVS operating system, and also assumes that one has some basic knowledge of SAS and how to use SAS to extract data from these files. The VIRA can also be helpful. The people at VIRA can also be of some assistance, although it's somewhat limited, and also in helping one to accomplish these goals of getting access to Austin, and once you're there, learning how to extract data from it. But if you are an investigator interested in obtaining data from Austin, your best bet is probably to hire a programmer who is experienced with SAS in order to get the data for you.
In a particular study, if I wanted to look at the vital status of the veterans in this study, how would I go about this using the Austin mainframe or other data files that are available?
One of the strengths of the VA databases is the availability of vital status information. And there's a nice short paper on the VIRIC website which examines the availability of mortality data on this Austin computer. There are basically two kinds of mortality data in the VA. There is, first of all, what's called the Burrell's death file, Burrell standing for Beneficiary Identification Record Locator System, which is basically a registration system for veterans who apply for benefits going back prior to the turn of the century. Part of this file, which is made available to VA researchers, is actually a death file which contains information regarding the veteran's service in the military as well as date of death. There is no information on cause of death. There is a second source of information which is not as extensive, and that is involved in the for veterans who are hospitalized, and if they die during hospitalization or in some time period thereafter, that death may also be recorded in the PTF section of the database. So this VIRIC document explains a little bit about various mortality databases both within and without the VA that are available, and I think is an important introduction to assessing vital status in general.
If my study involved inpatients and outpatients that were receiving pharmaceuticals or having laboratory values measured, would that data be available to me as well?
It's available in another source, that is at the Pharmacy Benefits Management Program at Hines in Chicago, Illinois. And one has to make separate application to use this database, and would involve linking whatever current data you have with Pharmacy Benefits Data Management Database, what they would provide to you for a given list of patients. This is separate from Austin, and it involves an application process which is described on the VIRIC website.
Okay. Another area that I would be interested in would be cost data. Is there a source for cost data for procedures, for laboratory tests, for pharmaceuticals? How would I go about getting that information?
There is a separate website called the Health Economics Resource Center, which is a kind of comparable to VIRIC, and it has the same website address, except it's www.herc.research.med.va.gov, and it has excellent descriptions about the methodology and actual procedures used in establishing cost of procedures and cost of medical care in the VA.
Is the VA data reliable?
Well, I think it's become increasingly so over time. There are some studies which have shown that the data on the inpatient side are more reliable than those on the outpatient side. But I think in the last 5 or 6 years there's been strong efforts to improve the collection of outpatient care data, which kind of go along with the increasing number of veterans who are receiving outpatient care in the VA. So I think one has to always be cautious, but these data represent a tremendous opportunity for one's research career, so to speak.
Dr. Maynard, thank you very much.
Thank you, Dr. River.